Hi, today we're tackling a problem called find all triplets with zero sum. We're given an array of integers. Our task is to find all triplets of indices I, j, k such that the sum of the elements at those indices, I plus j plus k, equals 0. There are a few key conditions to keep in mind. The indices I, j, and k must be distinct, meaning I cannot equal j cannot equal k, and k cannot equal I. The triplets must be returned in sorted order, so I must be less than j, and j must be less than k. If no triplets sum to 0, we return an empty set of triplets. Let's look at an example. Suppose our array is 0, -1, 3, 2, -3, 1. We need to find triplets of indices where the sum is 0. After checking, we find two triplets. Indices 0, 1, 5 give 0 plus -1 plus 1, which equals 0, and indices 3, 4, 5 give 2 plus -3 plus 1, which also equals 0. So, our output is the set of triplets, 0, 1, 5, and 3, 4, 5. Another example. If the array is 1, -2, 1, 0, 5, the only triplet is indices 0, 1, 2, because 1 plus -2 plus 1 equals 0. If the array is 2, 3, 1, 0, 5, there are no triplets that sum to 0, so we return an empty set. Approach. To solve this problem, we'll use sorting combined with the two-pointer technique. Here's the step-by-step approach. First, we sort the array in ascending order. Sorting helps us use two pointers effectively to find pairs that sum to a specific value, and it ensures our indices can be processed in a way that naturally satisfies the condition I less than j less than k. Next, we iterate through the array to fix the first element of the triplet. Let's call its index I. For each I, we need to find two other elements at indices j and k, where j is greater than I and k is greater than j, such that array at I plus array at j plus array at k equals 0. Since array at I is fixed, we need array at j plus array at k to equal minus array at I. This reduces the problem to finding two numbers in the remaining array from I plus 1 to the end that sum to minus of array at I. To find these two numbers, we use two pointers, one starting just after I, let's call it left, and one at the end of the array, call it right. Since the array is sorted, we can calculate the sum of array at left plus array at right. If the sum equals minus of array at I, we found a triplet, I, left, right. Add it to our result and move both pointers, left forward and right backward, to look for more pairs. If the sum is less than minus of array at I, the sum is too small, so we increment left to increase the sum. If the sum is greater than minus of array at I, the sum is too large, so we decrement right to decrease the sum. To avoid duplicates, if we find a triplet, we skip over any duplicate values at left and right. Also, if array at I equals array at I minus 1, we skip the current I to avoid duplicate triplets. Finally, we return the list of all triplets found. Let's try run this with the array 0, -1, 2, -3, 1, which has indices 0 to 4. Step 1. Sort the array. Sorting gives us -3, -1, 0, 1, 2. The indices are now based on the sorted array, but we'll track the original indices. Step 2. Iterate over I from 0 to length -3, since we need space for j and k. Length is 5, so I goes from 0 to 2. For I equals 0, array at I is -3, original index 3. We need array at left plus 1 array at right to equal minus of -3, which is 3. Set left to I plus 1, which is 1, and right to the end, which is 4. Left at 1 the value is -1, original index 1. Right at 4 that is the value is 2, original index 2. Sum is -1 plus 2 equals 1, which is less than 3. Increment left. Left at 2 the value is 0, original index 0. Right at 4 the value is 2, original index 2. Sum is 0 plus 2 equals 2, less than 3. Increment left. Left at 3 the value is 1, original index 4. Right at 4 the value is 2, original index 2. Sum is 1 plus 2 equals 3, which equals 3. We found a triplet, original indices 3, 4, 2, sort them to 2, 3, 4 to satisfy I less than j less than k. Add 2, 3, 4 to our result. Increment left, decrement right. Left at 4, right at 3. Pointers cross, stop. For I equals 1, the value is array at I is -1, original index 1. Target sum is minus of -1 equals 1. Left at 2, right at 4. Left at 2, the value is 0, original index 0. Right at 4, the value is 2, original index 2. Sum is 0 plus 2 equals 2, greater than 1. Decrement right. Left at 2, the value is 0, original index 0. Right at 3, the value is 1, original index 4. Sum is 0 plus 1 equals target. Triplet, original indices 1, 0, 4. Sort to 0, 1, 4. Add 0, 1, 4 to result. Increment left, decrement right. Left at 3, right at 2. Pointers cross, stop. For I equals 2. Array at I is 0, original index 0. Target sum is 0. Left at 3, right at 4. Left at 3, the value is 1, original index 4. Right at 4, the value is 2, original index 2. Sum is 1 plus 2 equals 3, greater than 0. Decrement right. Left at 3, right at 2. Pointers cross, stop. Step 3. Result is 0, 1, 4, and 2, 3, 4. Pseudocode. Return empty list if less than 3 elements, if n less than 3. Return empty triplets. Create list of value, index, pairs, and sort by value. Sort pairs by value. Fix first element. Use 2 pointers for the rest. Skip duplicates for first element. Target sum for the other 2 elements. Found a triplet. Store indices in sorted order. Add indices to triplets. Skip duplicates. Time and space complexity. Time complexity. First, sorting takes big O of n log n, where n is the array length. For each I, the 2-pointer technique scans the remaining array in big O of n time, and I runs from 0 to n minus 3, so that's big O of n squared for the loop. Overall, big O of n log n plus n squared equals big O of n squared. Space complexity. We use big O of 1 extra space for pointers, plus big O of n for storing the result and the index mapping. So, excluding the output, it's big O of n. This approach efficiently finds all triplets while ensuring the indices are distinct and sorted, making it a great application of sorting and 2-pointers. Thanks for learning with me today.